Here's something I don't hear enough about in high-density interconnect or HDI design. When you place a dense microvia field under a ball grid array or BGA chip to break out all those fine-pitched pins underneath the chip, every one of those vias punches an antipad or a clearance hole through your power and your ground planes in your PCB stackup. Individually, each pad is tiny, but underneath a 0.4 millimeter BGA with hundreds of pins, you end up with something CR circuits calls a Swiss cheese effect in the planes. That creates a slightly fragmented plane, and a fragmented plane does not deliver the same power that a fully solid plane does. Today we're going to look at what that actually means for your board and power delivery and how you can detect this before your PCB goes for manufacturing. What we're looking at here is the current density on a plane layer. In a healthy solid plane, you expect to see current and current density flowing evenly across the layers of the PCB, evenly across that copper. The current would flow smoothly from the vias and toward their intended load in the circuit. But look at what's happening in the BGA region. If I zoom in here, the current is denser in some areas and not as dense in other areas under the BGA. And if I show vectors, the current has to navigate around these antipad shapes on this plane. Now, in a sparse area of the PCB, that is not so much a problem. Like if we go in this area, there aren't a bunch of microvias, then the current is distributed very evenly. You'll see a more direct flow from one area to another area straight across and not having to navigate around the vias. But here with the antipads, they need to navigate around those antipads. And here's another example of how the current more or less evenly distribute itself, flowing from one major region to the next. But if we zoom in here where there's denser microvias and vias being routed closely together and you have these larger antipads, these antipads stack up, especially under a tight fine pitch BGA. The effective cross-section copper region of that plane or whatever that copper shape is reduced because of those antipads from all those microvias. The current is being funneled through the area that's left between the antipads. You see that here? And then you can see the density of the current increase at those narrow copper bridges. And so when you fragment your planes, right? Like how you have over here, and it's not a full solid plane, like on this power plane. This is what it looks like electrically. The effective impedance of the plane goes up, especially in certain areas, because the current path is being constricted. For a ground plane, this is going to look like an increased impedance in said plane because it's adding inductance to the return path. For a power plane, like the ones that we're looking at right here, this is going to increase your voltage drop, especially between your decoupling capacitors and your component power pins. Now, your decoupling capacitors should be right on your power pins, so I don't expect that to be a problem so much. But if you are delivering power from, say, a USB connector on the edge of the PCB and expect it to get all the way to the chips in the center of the PCB, you're going to encounter some voltage drop by splitting up your planes too much or not shaping them well. And this is what different areas of voltage drop may look like. In the red areas, that's our 5 volts that we expect, and then 5 volts gets to the areas we want them to. But notice how in some areas the voltage does drop to 3.3 volts, which is intentional in many areas, and a 2.7 volts, but there can be some slight variation. We need to pay attention and check for all of these. The design principle from this is something that Dr. Bogatin mentions very clearly in various papers and design guides. Even in high density interconnect or HDI PCBs, providing a continuous return path is non-negotiable. And in HDI boards, it's actually harder to maintain that principle and to enforce that because you have so many fine pitch components and BGAs that force you to have to use vias and microvias and small structures in tight areas. You get more via transitions and antipads concentrated in the same area. So what do you do about this? Well, there are two things you can do. One of them is antipad sizing. You can reduce the size of your antipad so that they're not as large, so your currents don't have to navigate as quite a wide as area to get through your field of vias. Less copper removed on the PCB means less fragmentation per via, more current can flow through the PCB copper. The other solution is regularly placing your power and ground vias in a staggered pairwise fashion next to each other, and not just placing grounds around the periphery of the PCB shape. So you want to place those power and ground vias throughout the underside of that BGA. That will reconnect your planes through the areas within the BGA or whatever your dense region is, your dense area of vias, and it gives the current more paths to flow through, and not just horizontally or on that plane, but vertically as well. And that's exactly what they did here in this design. Notice how the power and grounds are spread out amongst each other. If you look at this thing, not on a log scale, you have like little binary hot spots, but here you've got your ground distributed evenly and properly. There's a ground for every single other pad and via, alternating between these pads, these microvias and vias from 1 to 4, your blind and varied vias as well. So from layer 1 to 4, from layer 4 to 7, 1 to 5, 7 to 10, and your grounds in between each of them. What this does is that helps distribute that current more evenly, not only in the horizontal, but in the vertical Z axis of your PCB. You're also lowering the inductance of the copper area or plane, whatever you're doing this in, right? You can have these vias that come together as far as the antipad is concerned, and see, naturally that is going to up your current density in some areas. So there's that, but there's a lot of ground. This is all ground around here on the copper area. Now, when they place these ground vias, they're doing double duty. Not only are they providing more power delivery through your PCB, right, by providing more paths to ground, it's also closing the return current loop for current and signal transitions. So these ground vias are doing a fantastic job when you intersperse them. If you put them only on the edge, you're going to increase your impedance. It's not really going to matter as much, okay? You want your grounds in between each of your signals. Okay, I think I preached that enough. Just know that one placement decision or style or principle solves both problems, signal integrity and power integrity. Plane fragmentation in HDI design is one of those failure modes that is completely invisible to the design rule check. Technically, the clearances are all legal, right? You've correctly defined your vias as well. They're manufacturable. But you risk certain areas, especially under BGA components, of turning your PCB or certain parts of your PCB planes into something like Swiss cheese because of the antipad accumulation and how close they are. And your power delivery and return paths could suffer because of it if you're not careful. Using this analysis is how you get to see the impact of those decisions. And once you see it, the fix is pretty straightforward. Minimize your antipads. Distribute your power and ground via through the field, not just around it. Do those things and you get the full benefit of proper HDI design. Lower inductance, better power delivery, and cleaner return paths.